can I say? We have two speakers who are the foremost experts on the messaging layer security standard, also known as MLS, and its implementation in XMTP. We're going to do a deep dive, and I hope you have your questions and topics queued up for this huge opportunity that we have today. But first, I'd love for Eric with XMTP GTM to share some important announcements with us. Eric? Are muted, or we don't hear you, Eric. Okay. Well, you know what? Maybe we can just we could just take a look at the slide. I'm sorry, Eric.
All right, how about now?
Oh yeah, that's great. That's great.
Hey, sorry about that, guys. Awesome. Hi, everybody. Excited to share. We'll be at EthCC next week. So we'll be dropping in, and we have some awesome speakers lined up. Nick from our team will be going over MLS even more in depth as well. That we'll be going over today. We'll be hanging out at a hacker house on Tuesday, July 9th. So feel free to stop by. We'll be jamming out. Fabri, me, and Peter will be there talking about frames and building there. So come hang out with us on Tuesday. And then on Wednesday, we'll be with MetaMask and highlighting a spotlight there. We feature as a panelist. I think Matt will be speaking and sharing some insights about building with Web3 applications and products. Feel free to hit me up on Converse, heyeric.eth. Would love to meet. We'll be hanging out all week, seeing some great events, and planning some great stuff. So hit me up there, and we'll be seeing you all soon. So just wanted to highlight that. Thank you.
Fantastic. Thank you, Eric. All right. Well, here we go. First, I'd like to introduce you to Dr. Franziskus Kiefer. He is the CEO of Cryspen. Now, Cryspen is a consulting studio, and they specialize in privacy and cryptography solutions. Cryspen is the cryptographic integration partner for the MLS integration with XMTP. And I think we'd like to kick off today's discussion with a deep dive with Franziskus on MLS. Would you like to take it away?
Yes. Well, thanks for having me. And great that I never use any doctor title, but thanks a lot. So I have a couple of slides here on what MLS is and why we use it and why we think it's a good thing to use. But I don't want to talk too much, because I think it's more useful if you actually have questions for me that I can answer, rather than rambling about MLS, which I could probably do for days. So you might be familiar with protocols like Signal or something, and that's essentially what we have on the left side on the slide here is really the core of what Signal is doing, which is doing a couple of Diffie-Hellmans to negotiate a key. And that, of course, isn't great if you actually want to have group conversations. And so Signal was an awesome protocol, and still is an awesome protocol, but it does not have exactly something for group conversation where you can exchange a key in a group. And so what Signal used to do, or what many messengers used to do in this case, is essentially just build up one-on-one conversations. And that, of course, as you see on the right side, gives you n squared number of keys that you have to exchange, which isn't great because that doesn't scale. And so really, we needed some better protocols, but at the same time, there hasn't been any prior art really, either in research or in industry, to design a protocol like this. So really what MLS is, it's the first of its kind. And as such, it's also sort of an interesting one for the IETF to standardize, actually. So I also have a slide on the standardization stuff, but usually protocols are being standardized once they're a little further along. But that also gives you sort of like a chicken and an egg problem where like no one is really doing it, so no one is interested in it, no one is looking at it on like how secure is it. So, well, the ITF went ahead and started standardizing something, and that actually created an entire branch of like research around these type of protocols, and also, well, implementations, and now also actually deployments, like here with XMTP. And so if you can go to the next slide. Yes, so really the core of what MLS is doing is not so much exchanging that key, but the core of MLS really is about building a consistent view of the group so that everyone can agree on what the group looks like and then exchange a key within that group. But really the core is that what we have on the left side here, which is the wretched tree, which is essentially every member in that group is, you can think of it as a leaf node in that tree. And because, as we all know from like computer science 101, if you have a tree, we get like logarithmic size for the height of the tree. And because that is where the performance comes from, because essentially the root of that tree is the key that we want to exchange in that group. And then we have like a complicated key schedule and other stuff on there. And if you are interested in how the rest of the actual key derivation and things work, feel free to ask. But I don't think that's the most exciting part, because that's more or less standard how that's being done. Really, the interesting part is the left-hand side, the wretched tree in here. And so then the question is, of course, like, if we design a protocol like this, what is it actually good for? Like, what are the properties and guarantees we get from it? And that's one of the very open questions beforehand, because there hasn't been any protocol like this. And how do you actually define security properties on a group protocol like this? Because it certainly can't be the exact same properties that you have for one-on-one conversations. And in the end, the properties are similar on a high level, but very different on a low level. If you can go to the next slide, there we have the picture on what the main two security properties of a protocol like MLS are, and that is forward secrecy and post-compromise security, essentially. And those are sort of symmetric properties, where essentially we say forward secrecy is if we have a compromise of a device and keys are being leaked, that everything that came before that point, so all messages that have been exchanged before, are still secure. And I think that's a very desirable property. But this is actually not what comes from the main part of MLS. So the main complexity of MLS has nothing to do with this one, because this one is easy, so to say. Because, I mean, as you're all aware, doing blockchains and things, if you hash forward, you can't go backwards. So essentially, forward secrecy is essentially just hashing the key and deleting out keys. And in that way, you get forward secrecy. But the more interesting one, really, and what most of the MLS protocol really is dealing with, is post-compromise security. And that is the question, how do we get after a compromise, after some device was compromised for some time, can get back to a secure state? And that is what we call post-compromise security, and what is being done by updating the group state. And that's really where most of MLS's complexity comes from, because here it doesn't help to ratchet forward, because the attacker has that key in time and can keep hashing. And so if you would just keep hashing forward, the attacker could do the same. And so this is the place where we have to do expensive asymmetric cryptography. And that's where the tree comes in, and where we try to encrypt something to the highest level in the tree so that the other parties can decrypt with a key that's hopefully not being compromised. And so that's essentially where we try to break this forward hashing by adding new randomness and encrypting that to like a key that's not being compromised. And those are essentially the two main properties people would like to have from a protocol like this. If those are the right ones or not, I don't know. You can tell me if you would like to see something else. And I think there are also interesting things in here about expectations, because what a cryptographer sees as forward secrecy is something very different from what many people actually expect. Because this is not about actually the message not being available, because usually the message is being decrypted and you have that locally. And so even if you throw away the key and an attacker can't decrypt, if they get access to your device, they get the message, obviously. So what many people actually expect from forward secrecy is something more like ephemeral messages or something that are being deleted after some time. But I think it's always important to kind of be very clear on what kind of properties to actually get, and oftentimes they don't match up exactly. So yeah, also if there are questions about that, feel free to ask. So much about sort of like some of the core details. I just want to give essentially hints on where might be interesting bits and pieces in the protocol, and then you can ask me more. But if we go to the next slide, we have some detail on what it actually takes to become a protocol like this. So I stole some of these slides. So this one is actually from an RWC talk from some other folks that were involved in MLS. So this is the timeline of how MLS came about and how the RFC 9420 came into existence. And you see, it takes some time. So 2017 were sort of like the first discussions on, okay, maybe we want to do something here. And roughly a year later, there was the BOF, which is sort of like the initial thing at IETF where we say, okay, now we actually start working on something towards something. So 2018, which is a couple of years ago, is when MLS was initially being started. And then it took essentially 3 years to get to something that looks very close to what we have now. Of course, there were still like changes later on, but roughly 3 years of design process within the IETF. And 21, we had the first people with Cisco starting to ship something. 2022, Ring Central also started shipping something, and a year later, roughly, we had the RFC. So here you also see people start shipping these things before they are done, which is, well, these type of processes just take a long time, and usually you don't want to wait that long. And so, of course, that also means you have to be able to upgrade and like get new versions in. But if you want to have a standardized protocol, that's sort of like the price you have to pay. But you, of course, also get something for it. And so if you go to the next slide, I put some headings on essentially what happened around the standardization process. So starting with the TLS standardization of TLS 1.3 a couple of years ago, the IETF, at least in some areas, started to have a much closer collaboration also with universities and researchers to make sure that what is being standardized is also safe to be used. And MLS here followed a very similar path, and there was lots of collaboration. And during the standardization already, people started writing paper on like what works, what doesn't work, what are the security properties we get from it. And also like there's a lot of input like feeding back to the standardization process, making sure what is being standardized is secure in the end. And there's still being like papers being written about MLS, but these I think are some of the more interesting ones. If you want to go, these are all on eprint.iecr.org. All of them are published in like big conferences and stuff, and they really informed on like how the MLS protocol was developed. And yeah, well, then you might ask also like, okay, and who is using it now? Is it only XMTP? or are there other like notable users or like interest in it? And if you go to the next slide, I put some, I think, of the more interesting ones on there. I already mentioned Cisco and Ring Central. So on the right side, you see the WebEx version. So there is MLS in WebEx already, and you can use it. This one even has like a post-quantum secure version in it, but the regular version is just a regular MLS implementation. It's currently in. You can currently use it for calls. It's also being deployed for chat over time. That just needs more integration work. And Ring Central has it deployed widely as well across all their products. And then on the top here, well, because I'm in Germany, the German government more or less mandates MLS for classified communication in messengers. So there are lots of players, also bigger players, who are essentially betting on MLS. And even though I think we haven't seen any huge deployments yet, I think there's lots of buy-in from many parties, so that I think like there's no way for MLS to fail. At the same time, there will be like a new version and there will be improvements because it's the first iteration of the protocol. There are always things that are not like perfect. But yeah, I doubt that MLS will go away anytime soon. And yeah, so I think with that, I'm kind of done with what I wanted to talk about. But I hope you all have like interesting questions.
Great. Thank you so much, Francisco. Any thoughts from the group? And we also have Rich following on with the relationship between MLS and its implementation in XMTP.
I wanted to check my head math. So under Signal's algorithm that you described, there'd be something like 100 keys for a 10-person group, whereas with MLS, it's somewhere between like 1 and 2 dozen. Is that correct?
Yes and no. So what most messengers are actually doing nowadays is something called sender keys, where you don't have to do that anymore, but essentially you define a key, send it to everyone, and then start using that one instead to get around this super inefficiency. But of course, sender keys has lots of other problems in terms of like the security properties. So sender keys does not satisfy forward secrecy and post-compromise security as MLS or Signal does.
Great. And any other questions? Hi, Paul.
Hey everyone, can you hear me? Yes. Hello everyone, thank you very much for the presentation. I have two questions, maybe a little bit naive, but the first one is around post-compromise security. Like technically, it seems to me that basically you're not excluding someone from a group. You're kind of creating a new group without this person. So this is my understanding. I just wanted to make sure it was somehow correct. And the second question would be around the size of groups and the theoretical size of groups in terms of the ability for the protocol to have like, I don't know, like how many people in a group while keeping some efficiency.
Yeah, great question. No, so the first one, so maybe post-compromise security, I think is a maybe somewhat difficult to understand notion. So the idea is that some user device is being compromised at some point in time, but then whatever you get like a security update from your OS or something, like the attacker is gone again. So like your device is safe, and now we would like to get into a good state there. So it's not necessarily about excluding someone, but it's about that a device has been insecure for a certain point in time, and now it's not anymore. So how do we get it back to something secure? How do we get to a key that is not known to the attacker anymore? And I mean, I also have my issues with some of these security notions, because the question is like, what is your threat model for compromising keys? Because in this case, we have to assume that essentially some of the long-term keys are not being compromised. And that's where, for example, messengers could put some of the keys into some secure enclave, so they are less likely to be compromised, but the keys that are being used all the time are just stored regularly. So maybe they are compromised, but the other ones are not. And so you can encrypt to like those keys that are not being compromised, and in that way get back to a secure state. Does that make sense?
Yeah. No, I would have to understand deeper the way it works, but in like broadly, yes.
Okay. And then what was the second one again? Sorry.
About the size of the groups and the ability to keep the performance of a messaging service, which is expected to be very high in groups of tens, hundreds, or even thousands of people.
Yeah. So I think XMTP has like a 400 user group limit right now. But I think those limitations are coming from something else. So MLS was designed, well, there were numbers in the room which are like 100,000. I doubt that 100,000 is realistic, but I think something like 20,000 should certainly be doable. And at least from the numbers I've done like with benchmarks and things, that should definitely be okay. So I think at that point we have like lots of other problems in like delivering messages and encodings and things, where not necessarily like the crypto here is the issue. And then I think it's also a question about like these big groups are oftentimes more broadcast rather than something where everyone is sending messages. And for that, really, MLS isn't very good. So I think for those groups, we should do something else, or, well, not necessarily something else, but a variant of MLS that is more efficient for those cases, because we're doing lots of things that are really not necessary for those cases.
Yeah, I see definitely. Keeping MLS is also a matter of security and ability to encrypt the conversations. So yeah, it's likely that even if you have like thousands of people in a group, anyways, it's not going to keep being private for a while. Yeah. So thank you very much.
Great. Thank you.
Groups the use case for sender keys that you mentioned, or are sender keys being used for different kind of groups by other apps? And if so, what apps are using them?
So WhatsApp is certainly using sender keys. Signal is using some version of sender keys that's like slightly better. And like sender keys are good in a sense. So, for example, all the matrix protocols, like the Olm, MacOlm, is the group version, is using sender keys as well. The advantage of sender keys is sort of that you can encrypt a message and just send it out, and be certain that the other side can decrypt it. Because with something like MLS, where you have to agree on a group state first, that might be difficult, right? So if you actually, for example, if you update the group state, then you have to make sure everyone get that group state before you can send a message in this new state. And that might introduce a delay, or you have to wait sending that message. And that's something you can't, like with sender keys, you could just send something out and it works. And of course, something like broadcast groups, for example, are much better with sender keys, because really you only need like maybe 2 or 3 keys for the people actually sending messages, not for everyone else.
Great. Thank you very much. All right. Well, maybe what we can do now is continue on with a discussion about how MLS and XMTP work together, and then we can follow on with more Q&A after that. But I'd like to introduce you to Rich Hua. He is an XMTP core developer who helped architect and build the MLS integration with XMTP. Rich, would you like to take on another deep dive?
Sure. Hey everyone, how's it going? Can you hear me?
Yes.
Great. So yeah, I'm gonna be talking. I'll try to be quick. Talking about how we've integrated Open MLS into XMTP. So to kind of summarize what Franziskus talked about, the core of our protocol is this library called OpenMLS, and essentially this is using an IETF standard with security properties comparable to Signal that is a little bit more scalable and more secure for groups. We have built layers on top of that. So the core of our protocol is a Rust library called libxmtp. And then we have laid above that several platform and language specific SDKs, for example, React Native, iOS, Android, and so on. So one of the things that we've added here is persistence and networking. Compared to the previous version of XMTP, we've implemented the client-side caching for you. So that's something that you no longer need to do. So the next natural question is, what else? Like, where does MLS end and where does XMTP begin? So we can go to the next slide. So to kind of like give a high-level overview, MLS is a protocol that describes the shape of the messages, like what the messages should look like, that are exchanged between cryptographic key pairs. So there's still a lot that is left up to the implementer. And there's two pieces specifically here. One is called the authentication service. Basically, what identities do the cryptographic key pairs represent? And how do we map between cryptographic key pairs and users? So to give an example, with apps like Signal or WhatsApp, a user is represented by a phone number. So then they need to do some kind of mapping between a cryptographic key pair and a phone number. The other piece that is not defined is the delivery service. So once a message is constructed, how does it reach the other identities in the system? And then to answer that question, we need to go into backend design. Okay, next slide. So we can talk about the authentication service first. So in XMTP, users are not represented by phone numbers, they're represented by wallets. So XMTP is a protocol for wallet-to-wallet communication. And there's a few properties that we want to achieve. We want it to be interoperable across naming systems. So it should work with Farcaster FIDs, it should work with Lens, ENS, Unstoppable. Users need to be able to have multiple wallets. We need to support both smart contract wallets and EOAs. And we need to handle the fact that users may use multiple apps. On top of that, we need to make sure that registration is free and that the developer interface is simple. So we can look briefly at how we did that. Next slide. So this is a diagram of what a power user might look like. I think most users will not look like this, but mainly for illustration purposes. So I'll start from the bottom and make my way to the top. So at the bottom, we have this concept of an installation key. So a user may have multiple apps installed that are compatible with XMTP. And those apps might be on the same device, or they might be on multiple devices. So a user might have two XMTP apps on their phone and one on their laptop. And what we want to achieve is every app has a separate cryptographic key pair. And what that does for us is it makes sure that, for example, if app B turns out to be compromised or malicious, that the user can essentially revoke or turn off app B without it affecting app A. So that's a very important separation that we're achieving here. It also enables some of the properties that Franziskus talked about earlier, post-compromise security and forward secrecy. We know that if you delete the installation key on one device, there are no other devices that it exists on. So the next layer up on the tree is wallets. And we establish a link between a wallet and an installation key using a signature. So when a user signs in on a new device or a new app that uses XMTP, we request that user to sign their installation key with the wallet. And that essentially is a declaration from the user that I grant this app permission to message on behalf of my wallet. And this is actually a slight improvement over apps like Signal or WhatsApp. Because their identities are represented by phone numbers, there's no way to cryptographically prove a link between a key pair and a phone number. So for non-security conscious users on that platform, they essentially have to trust the server that they are talking to who they think they are talking to, which is not the case for XMTP. Okay, so the final layer above that is the inbox ID. This is just a very lightweight abstraction that we've added to allow the user to attach multiple wallets to an account. The way this works is basically a two-way signature between an existing wallet and a new wallet that you want to add. So every arrow in this diagram represents essentially a cryptographic link. Next slide. So one thing I want to emphasize is this is all happening under the hood. This is not something that an average developer needs to worry about. We've handled this for you. We have simple APIs for registering a new account, and we will request those signatures on your behalf. And there are more details about this whole process in XIP 46. So yeah, you're welcome to look into that. Next slide. Okay, so then the final piece to talk about is the delivery service. Basically, how do we make messages go from point A to point B? MLS requires a delivery mechanism for all messages, and in particular, consensus ordering for commit messages. What this means is if I receive commits A, B, and C on my device, everybody else has to receive it in the same order. If they receive A and then C and then B, then our group chat will be broken. Next slide. So the delivery service today is a centralized one. It's a Go node with a Postgres database. And cryptography protects against payload forgery and tampering. So there's no trust required in ephemera or XMTP to prevent these things. However, trust is required in the current system to prevent payload reordering and omission. Next slide. So this is something that we are actively working to address. We are working on a decentralized system. So what this will consist of is an L3 blockchain for strictly ordered payloads, such as MLS commits. And this should be a very small subset of MLS messages. And then a peer-to-peer gossip protocol for loosely ordered payloads. And that allows us to essentially reduce cost and remove the requirement for trust in a centralized server. Next slide. So now we can talk about like the rollout. So MLS group chats are already available today on iOS, Android, React Native, and Node.js. We are sprinting to have MLS on web available by the end of Q3. We will have one-on-one chats fully switched over to MLS by the end of the year. There are certain back compatibility issues that we need to kind of take care of. And we are aiming to have the decentralized backend live by the end of the year. And that's about it for me.
Incredible, Rich. Thank you so much. I'm sure a lot of people appreciate the rollout slide, especially. Wonderful. Any any questions, any points of discussion after hearing both Franziskus and Rich?
Can I go first? I have a question. Anyone else? No. Okay. I actually have two questions. The first one is, again, just trying to make sure I understand the link between MLS and XMTP. Do I understand correctly if I say that on XMTP, each installation key is a user? Maybe I'm saying it wrong, but like in MLS, I mean, if I have 3 installation keys, MLS, the protocol, sees me as 3 different people in the conversation. Is that correct? Or by people, I mean like entities. Am I correct?
Yeah, that's the right intuition. MLS sees you as 3 cryptographic identities, and then the application, in this case XMTP, is responsible for saying that those 3 cryptographic identities represent the same person.
That's clear. Perfect. So I understood well. Thank you. And the second is a question. Like L1, 2, 3, 4, 5, 6, etc. Are the trendy things. I guess there is already quite a lot of work on your side. But I would be curious to know what are the criteria that will be sufficient in order to decentralize the thing. So if I say it in different words, putting something on chain is generally like the very first reflex that we all have in Web3. But the truth is, sometimes there are some things that need to be on chain in the way that we see it in general, but some other things can be either provable on a different chain or in a totally separate network with the right consensus mechanism. So basically, it might be a good discussion that could be longer, but if you say it in a few words, what are the criteria that are important to you? If we map the whole thing, what is the core principle that you need to actually achieve here?
Yeah, so there's 3 things I can talk about here. So I guess the core of the question is, what is the point of decentralizing? Like, what are we trying to achieve? And we can answer that in there's 2 properties that we want. The first property I can phrase as a question. If XMTP or ephemera dies tomorrow, like our backend stops running, will the protocol keep running? And if we've decentralized well, then the answer is yes. We don't need ephemera to exist for the protocol to keep running. The next question we would want to answer is, if the backend provider is malicious, let's say XMTP wants to do bad things on your behalf, or tamper with your data, or prevent you from sending messages, are they able to do that? What is required in order for the parties in the middle to essentially mess with your communications? And if we've decentralized in a good way, it becomes very, very difficult. We would require a lot of collusion between many different parties in order for that to be possible. So we've answered part of that question through cryptography, and then the other part of that question we are answering through decentralization. And then the final part is kind of like, why are we putting some of our stuff on a blockchain and some of our stuff off-chain? Essentially, what a blockchain gives us is the strongest properties that you can get. There's an incentivization layer. There is strict ordering of your data. So every node will give you the same order for the same data. But you're paying a lot more cost. So essentially, what we try to do is put your most important data on a blockchain, and the data that can be fudged a little bit, like the ordering doesn't matter too much. Like if it gets reordered, your conversation doesn't break. We can put that on a cheaper network, a gossip network that is off-chain. Does that answer your question?
Yes, it does, definitely. Thank you very much. These are very interesting conversations, I guess.
Yeah. Rich, can you talk briefly about the scale of gossip? Like if you're does it vary with the number of participants in the group, for example?
What do you mean by the scale of gossip?
So if I've got a group of 10 people, of 10 participants versus a group of 1,000 participants, when I have a group of 1,000 participants, I don't really need to see as many as large a percentage of the group sort of agreeing on the order of the payload.
Oh, I see. So the size of a group is not correlated to the size of the backend. So to be clear, we're talking about a backend that might consist of 10 different nodes. And every member of a group would be fetching their data from one of these 10 nodes. So a user sends a message that gets gossiped across those 10 nodes. And then anyone in the group can fetch that message from any of those 10 nodes. So the number of nodes does not scale with the group size. And the nodes are essentially separate parties to the group participants. Does that make sense?
Yeah, that makes sense. What I was referring to is the problem of collusion.
Yeah.
So if in a large group you have a much higher probability of collusion, so you want you want more, but not linearly more.
Yeah.
Confirmation that you've received the same amount of information as the same order of messages, for example, or the same number of messages as somebody else.
Yeah, okay. I can talk about collusion briefly. So with a gossip protocol, the way it works is whenever any node receives a message, it broadcasts that message out to every other node. So if in a network with 10 nodes, you can think of it like 10 people standing in a room. And whenever somebody essentially whispers a message to one of those nodes, that node will then kind of yell it out to the whole room. So if we're worried about a node censoring your data, all you have to do is whisper that message to more than one node. Just whisper it to 2 nodes, right? And one node might choose not to broadcast your data, but if any of the nodes that you essentially communicate with are cooperative, they will broadcast that out to everybody. So it's very hard to suppress information in a gossip network. Does that make sense?
Thanks, Rich.
Yeah.
Thank you so much, Rich.
Thanks.
Both of you excellent teachers. I appreciate that. Any other questions? And actually, we are at time for our meeting today. And, I think this recording we have running is very valuable, and folks have already been asking for it in the chat. And so we will get it up on YouTube and share it widely. And we do also have a community forum post that we'll put alongside it so we can continue the discussion there. I'm sure some questions may come up after people sit and digest a little bit. So again, so much thanks to Franziskus and to Rich for sharing their expertise with us today. Thank you, everyone, for joining and being a part of the community. All right. We will see you next time. Take care. Thank you.
Thank you.
Bye-bye.